Testing, can you hear me? Testing, can you hear me? Okay, so I am going to be reading about computer architecture again. I will continue reading the I/O and storage device chapter. Last stream, I was learning about the physical layer. I read about the synchronization sublayer, and this stream, I'm going to be learning about data link layer. Now we are ready to discuss the data link layer. The data link layer gets sequences of logical bits from the physical layer. If the width of the serial in parallel out register is n bits, then we are guaranteed to get n bits at one go. The job of the data link layer is to break the data into frames and buffer frames for transmission on other outgoing links. Secondly, it performs rudimentary error checking and correction. It is possible that due to electromagnetic interference, errors might be induced in the signal. For example, a logical 1 might be a logical 0 and vice versa. It is possible to correct such single bit errors in the data link layer. If there are a lot of errors and it is not possible to correct the errors, then at this stage, the receiver can send a message to the transmitter requesting for a retransmission. After error checking, the frame is ready to be forwarded on another link if required. It is possible that multiple senders might be trying to access a bus at the same time. In this case, we need to arbitrate between the requests and ensure that only one sender can send data at any single point of time. This process is known as arbitration and is also typically performed in the data link layer. Lastly, the arbitration logic needs to have special support for handling requests that are part of a transaction. For example, the bus to the memory URS might contain a load request as a part of a memory transaction. In response, the memory unit sends a response message containing the contents of the memory locations. We need a little bit of additional support at the level of the bus controller to support such message patterns. To summarize, the data link layer breaks up data received from the physical layer into frames, performs error checking, and manages the bus by allowing a single transmitter at a single time, and optimizes communication for common message patterns. Framing and buffering. The process in the data link layer begins by reading set of bits from the physical layer. We can either have one serial link or multiple serial links that transmit bits simultaneously. A set of multiple serial links is known as a parallel link. In both cases, we read in data, save them in serial in, parallel out, shift registers, and send chunks of bits to the data link layer. The role of data link layer is to create frames of bits from the values that it gets from the physical layer. A frame might be 1 byte for links that transfer data from the keyboard and mouse, and it might be as high as 128 bytes for links that transfer data between the processor and the main memory, or the main memory and the graphics card. In any case, the data link layer for each bus controller is aware of the frame size. The main problem is to demarcate the boundaries of a frame. Demarcation by inserting long pauses. Between two consecutive frames, the bus controller can insert long pauses. By examining the duration of these pauses, the receiver can infer frame boundaries. However, because of jitter in the I/O channel, the duration of these pauses can change and new pauses can be introduced. This is not very reliable. This is not a very reliable method, and it also wastes valuable bandwidth. We can fix the number of bits in a frame a priori. We can simply count the number of bits that are sent and declare a frame to be over once the required number of bits have reached the receiver. However, the main issue is that sometimes pulses can get deleted because of signal distortion, and it is very easy to get out of synchronization. Bit byte stuffing. This is the most flexible approach, and it is used in most commercial implementations of I/O buses. Here we use a pre-specified sequence of bits to designate the start and end of a frame. For example, we can use the pattern deadbeef to indicate the start of the frame, and 1, 2, 3, 4, 5, 6, 7, 8 to indicate the end of the frame. The probability that any 32-bit sequence in a frame will match the special sequence of the start and end is very small. The probability is equal to 2 to the power of minus 32. Sadly, the probability is still non-zero. Hence, we can adopt a simple solution to solve this problem. If the sequence deadbeef appears in the content of a frame, then we add 32 more dummy bits and repeat this pattern. For example, deadbeef gets replaced by deadbeef. The link layer of a receiver can find out that the pattern repeats an even number of times. Half of the bits in the pattern are a part of a frame, the rest are dummy bits. The receiver can then proceed to remove the dummy bits. This method is flexible because it is very resilient to jitter and reliability problems. These sequences are known as commas. Once the data link layer creates a frame, it sends it to the error checking module and also buffers it. Errors can get introduced in signal transmission for a variety of reasons. We can have external electromagnetic interference due to other electronic gadgets operating nearby. Readers would have noticed a loss in the voice quality of a mobile phone after they switch on an electric gadget such as a microwave oven. This happens because electromagnetic waves get coupled into copper wires of the I/O channel and introduce current pulses. We can also have additional interference by nearby wires known as crosstalk and changes in the transmission delay of a wire due to temperature. Cumulatively, interference can introduce jitter, introduce variability in the propagation time of the signal, and introduce distortion, change the shape of the pulses. You can thus wrongly interpret a 0 as a 1 and vice versa. It is thus necessary to add redundant information such that the correct value can be recovered. The reader needs to know that the probability of an error is very low in practice. It is typically less than 1 in every million transfers for interconnects on motherboards. However, this is not a very small number either. If we have a million I/O operations per second, which is plausible, then we will typically have 1 error per second. This is actually a very high error rate. Hence, we need to add extra information to bits such that we can detect and recover from errors. This approach is known as forward error correction. In comparison, in the backward error correction, we detect an error, discard the message, and request the sender to retransmit. Let us now discuss the prevalent error detection and recovery schemes. So in forward error correction, additional bits contain information to detect and recover from single or double bit errors if required. In backward error correction, we add additional bits to a frame, and these bits help us detect single or double bit errors. However, they do not allow us to correct errors. We discard the message and ask the transmitter for a retransmission. Since single bit errors are fairly improbable, it is extremely unlikely that we shall have 2 errors in the same frame. Let us thus focus on detecting a single error and also assume that only 1 bit flips its state due to an error. Let us simplify our problem. Let us assume that a frame contains 8 bits and we wish to detect if there is a single bit error. us number the bits in the frame as D1, D2 to D8 respectively. It is now added additional bit known as the parity bit. The parity bit P is equal to D1 XOR D2 XOR D3 all the way till D8. In simple terms, the parity bit represents the XOR of all data bits. For every 8 bits, we send an additional bit, which is the parity bit. Thus, we convert an 8-bit message to an equivalent 9-bit message. In this case, we have effectively added 12.5% overhead in terms of available bandwidth at the price of high reliability. Figure 13.22 shows the structure of a frame or message using our 8-bit parity scheme. Note that we can support larger frame sizes also by associating a separate parity bit with each sequence of 8-bit data bits. When the receiver receives the message, it computes the parity by computing the XOR of the 8 data bits. If this value matches the parity bit, then we can conclude that there is no error. However, if the parity bit in the message does not match the value of the computed parity bit, then we can conclude that there is a single bit error. The error can be in any of the data bits in the message or can even be in the parity bit. In this case, we have no way of knowing. All that we can detect is that there is a single bit error. Let us now try to correct the error also. To correct a single bit error, we need to know the index of the bit that has been flipped if there is an error. Let us now count the set of possible outcomes. For an n-bit block, we need to know the index of the bit that has an error. We can have n possible indices in this case. We also need to account for the case in which we do not have an error. Thus, for a single error correction circuit, there are a total of n plus 1 possible outcomes. N outcomes with error and 1 outcome with no error. Thus, from a theoretical point of view, we need log n plus 1, the ceiling of log n plus 1 additional bits. For example, for an 8-bit frame, we need 4 bits. Let us design 8-4 code that has 4 additional bits for every 8-bit data word. Let us start out by extending the parity scheme. Let us assume that each of the 4 additional bits are parity bits. However, they are not parity functions of the entire set of data bits. Instead, each bit is a parity of a subset of data bits. Let us name the 4 parity bit P1, P2, P3, P4. Moreover, let us arrange the 8 data bit and 4 parity bit as shown in figure 13.23. We keep the parity bits P1, P2, P3, P4 in positions 1, 2, 4, 8 respectively. 1, 2, 4, okay. We arrange the data bits in positions, okay. The next step is to assign a set of data bits to each parity bit. Let us represent the position of each data bit in binary. In this case, we need 4 binary bits because the largest number that we need to represent is 12. Now, let us associate the parity bit P1 with all the data bits whose position have 1 as their least significant bit. In this case, the data bits with 1 as their least significant bit are D1, D2, D4, and D5. D2, D4, and D5. We thus compute the parity bit P1 as D1 XOR D2 XOR D4 XOR D5 XOR D7. It is not clear to me why these bits in particular. Let us associate the first parity bit with all the data bits whose positions represented in binary have 1 as their least significant bit. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, I see. So wait, 1, 2, 3. 3 has 1 in the least significant bit. 3 is odd. 1, 2, 3, 4, 5. 5 has a 1 in the least significant bit. 6, 7. 7 has a 1 in the least significant bit. 8, 9. 9 same. 10, 11 same for 11. Okay, now I understand. Similarly, as you see, the second parity bit P2 with all the data bits that have 1 in their second position. Okay, so 1, 2, 3, 4. So P1 uses this. So P2 uses this. Alright. Table 13.2 shows the association between data and parity bits, and X indicates that a given parity bit is a function of the data bit. Based on this table, we arrive at the following equations for computing the parity bits. The algorithm for message transmission is as follows. We compute the parity bit according to equations 13.3 to 13.6. Then we insert the parity bits in the positions 1, 2, 4, and 8 respectively and form a message according to figure 13.23. According to figure 13.23. Okay. By adding the data bits, once the data link layer of the receiver gets the message, it first extracts the parity bit and forms the number of the form P, which is P4, P3, P2, P1. That is composed of 4 parity bits. For example, if P1 is 0, P2 is 0, P3 is 1, P4 is 1, then P is 1, 1, 0, 0. Subsequently, the error detection circuit of the receiver computes a new set of parity bits from the received data bits and forms another number of the form like this. So once the data link layer of the receiver gets the message, it extracts this, right? And this is subsequently the error detection circuit at the receiver computes a new set of parity bits. Ideally, P should be equal to P naught. However, if there is an error in the data or parity bits, then this will not be the case. Let us compute P X or P naught. This value is known as the syndrome. Let us now try to correlate the value of the syndrome with the position of the erroneous bit. Let us first assume that there is an error in a parity bit. In this case, the first 4 entries in table 13.3 shows the position of the erroneous bit in the message and the value of the syndrome. The value of the syndrome is equal to the position of the erroneous bit in the message. This should come as no surprise to the reader because we designed our message to explicitly ensure this. The parity bits are at positions 1, 2, 4, and 8 respectively. Consequently, if any parity bit has an error, its corresponding bit in the syndrome gets set to 1, and the rest of the bits remain 0. Consequently, the syndrome matches the position of the erroneous bit. Let us now consider the case of single bit errors in data bits. Again, from table 13.3, we can conclude that the syndrome matches the position of the data bit. This is because once data bit has an error, all its associated parity bits gets flipped. For example, if D5 has an error, then the parity bit P1 and P4 gets flipped. Recall that the reason we associate P1 and P4 with D5 is because D5 is bit number 9, and the two ones is the binary representation of 9 are in positions 1 and 4, respectively. Subsequently, when there is an error in D5, the syndrome is equal to 1001, which is also the index of the bit in the message. Similarly, there is a unique syndrome for every data and parity bit. So if P1 has an error, we have this syndrome. If there's an error in position 6, then we have this syndrome. Oh, I see. Thus, we can conclude that if there is an error, then the syndrome points to the index of the erroneous bit. Now, if there is no error, then the syndrome is equal to 0. We thus have a method to detect and correct a single error. This method of encoding message with additional parity bits is known as single error correction code. Let us now try to use the single error correction code to additionally detect double errors. Let us show a counterexample and prove that our method based on syndromes will not work. Let us assume that the errors in bits D2 and D3 are, now we have double errors. Syndrome will be equal to 0, 1, 1, 1. However, if there is an error in D4, the syndrome will be equal to 0, 1, 1, 1. Thus, there is no way of knowing whether we have a single bit error or a double bit error. Let us slightly augment our algorithm to detect double bit errors also. Let us add an additional parity bit P5 that computes the parity of all the data bits. And the 4 parity bits used in SEC code. And then let us add P5 to the message. Let us save it in the 13th position of our message and exclude it from the process of calculation of the syndrome. The new algorithm is as follows. You first calculate the syndrome using the same process as used for the SE single error correction code. If the syndrome is 0, then there can be no error. The proof for the case of a single error can be readily verified by taking a look at table 13.2. For a double error, let us assume that 2 parity bits have been flipped. In this case, the syndrome will have 2 ones. Similarly, if the 2 data bits have been flipped, then the syndrome will have at least 1 bit. Because no 2 data bits have identical columns in table 13.2. Table 13, okay. If 2 data bits have been flipped, then the syndrome will have at least 1 bit, because no 2 data bits have identical columns in table 13.2. Now, if a data and parity bit have been flipped, then also the syndrome will be non-zero, because a data bit is associated with the multiple parity bits. Because the data bit is associated with multiple parity bits. The correct parity bits will indicate that there is an error. Hence, if the syndrome is non-zero, we suspect an error. Otherwise, we assume that there are no errors. If there is an error, we take a look at the bit P5 in the message and also recompute it at the receiver. Let us designate the recomputed parity bit P5 naught. Now, if P5 is equal to P5 naught, then we can conclude that there is a double bit error. 2 single bit errors are essentially cancelling each other while computing the final parity. Conversely, if they are not equal, then it means we have a single bit error. We can thus use this check to detect if we have errors in 2 bits or 1 bit. If we have a single bit error, then we can also correct it. However, for a double bit error, we can just detect it and possible ask for the source of for retransmission. This code is popularly known as SECDED code, also from single error correction, double error detection, I think. All the codes described up till now are known as Hamming codes. This is because they implicitly rely on Hamming distance. The Hamming distance is the number of corresponding bits that are different between two sequences of binary bits. For example, the Hamming distance between 0011 and 1010 is 2. Number of corresponding bits that are different between two sequences of binary bits. So this 0 and 1 in the middle, they're in the correct, they're the same, right? But 1 at the start and 0 at the end, that is different. The start and end are different, so the Hamming distances too. Let us now consider a 4-bit parity code. If a message is 0001, the parity bit is equal to 1. The transmitted message with the parity bit is the most significant position is 10001. Let us refer to the transmitted message as the code word. Note that 00001 is not a valid code word, and the receiver will rely on this fact to judge if there is an error or not. In fact, there is no other valid code word within a Hamming distance of 1 of a valid code word. The reader needs to prove this fact. Likewise, for a single error correction code, the minimum Hamming distance between code words is 2. For a SECDED code, it is 3. Let us now consider a different class of codes that are also very popular. Cycle redundancy check codes. CRC codes are mostly used for detecting errors, even though they can be used to correct single bit errors in most cases. To motivate the use of CRC codes, let us take a look at the patterns of errors in practical I/O systems. Typically, in I/O channels, we have interference for a duration of time that is longer than a bit of period. For example, if there is some external electromagnetic interference, then it might be fast for several cycles, and it is possible that several bits might get flipped. This pattern of errors is known as burst errors. For example, a 32-bit CRC code can detect burst errors as long as 32 bits. It typically can detect most 2-bit errors and all single-bit errors. The mathematics behind SRC's codes is complicated, and interested readers are referred to text on coding theory. Let us show a small example in this section. Let us assume that we wish to compute a 4-bit CRC code for an 8-bit message. Let the message be equal to 1011 0011 in binary. The first step is to pad the message by 4 bits, which is the length of the CRC code. Thus, the new message is equal to 1011 0011 0000. The CRC code requires another 5-bit number, which is known as the generated polynomial or the divisor. In principle, we need to divide the number represented by the message with the number represented by the divisor. The remainder is the SRC code. However, this division is different from regular division. It is known as modulo 2 division. In this case, let us assume that the divisor is 11001. Note that for an n-bit CRC code, the length of the divisor is n plus 1 bits. Let us now show the algorithm. We start out by aligning the most significant bit of the divisor with the most significant bit of the message. If the most significant bit of the message is equal to 1, then we compute an XOR of the first n plus 1 bits and the divisor and replace the corresponding bits in the message with the result. However, if the most significant bit is 0, we do not do anything. In the next step, we shift the divisor one step to the right. Treat the bit in the message aligned with the most significant bit of the divisor as the most significant bit of the message and repeat the same process. We continue the sequence of steps till the least significant bit of the divisor is aligned with the least significant bit of the message. We show the sequence of steps in example 156. At the end, the least significant n 4 bits contain the SRC code. For sending a message, we append the CRC code with the message. The receiver recomputes the CRC code and matches it with the code that is appended with the message. Show the steps of computing a 4-bit CRC code where the message is equal to 1011 0011 and the divisor is equal to 11001. So this is the original message. We add a padding and then we do a division, right? So when we do a division, so the most significant bit of the message is equal to 1. We compute an XOR of the first n plus 1, 5 in this case, bits and the divisor, and replace the corresponding bits in the message with the result. So here the most significant bit is 1. And then we do an XOR, right? Compute an XOR of the first n plus 1 bits, alright. We do an XOR, 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 XOR. And then what happens? If the most significant bit is 0, if the most significant bit is 0, we do not do anything. When they say most significant bit, they mean like within, they mean over here, or most significant bit starting from here. Because they're doing XOR here as well, right? They're doing XOR again, and then they do XOR again. I want to see a case where they don't do XOR. In the next step, we shift the divisor one step to the right, treat the bit in the message aligned with the most significant bit as of the divisor as the most significant bit of the message and repeat the process. Okay. So the one that is aligned with the divisor, they want the most significant bit of that. In this case, it's a 1, so we do an XOR. Over here, this is 1. This over here, this is a 1. But they're shifting 2 positions, not 1. Why are they shifting 2 positions? Oh, because it's a 0. It's a 0. They don't do anything, so they shift again. That's why they're shifting 2 positions. Over here, it's a 0, so that's why they're shifting 2 positions. Let us now consider the problem of bus arbitration. The word arbitration literally means resolution of disputes. Let us consider a multi-drop bus. Let us consider a multi-drop bus where you can potentially have multiple transmitters. Now, if multiple transmitters are interested in sending a value over the bus, we need to ensure that only one transmitter can send a value on the bus at any point of time. Thus, we need an arbitration policy to choose a device that can send data over the bus. If we have point-to-point buses where we have one sender and one receiver, then arbitration is not required. If you have messages of different types waiting to be transmitted, then we need to schedule the transmission of messages on the link with respect to some optimality criteria. We need to ensure that only one transmitter sends values on the bus at any point of time. Secondly, we need to ensure that there is fairness and the transmitter does not need to wait for an indefinite amount of time for getting access to the bus. Furthermore, different devices connected to a bus typically have different priorities. It is necessary to respect these priorities also. For example, the graphics card should have more priority than the hard disk. If we delay the messages to the graphics card, the user will perceive jitter on her screen, and this will lead to bad user experience. We thus need a bus allocation policy that is fair to all transmitters and is responsive to the needs of the computer system. This bus allocation policy is popularly known as arbitration policy. We envision a dedicated structure known as an arbiter, which performs the job of bus arbitration. All the devices are connected to the bus and to the arbiter. They indicate their willingness to transmit data by sending a message to the arbiter. The arbiter chooses one of the devices. There are two topologies for the connecting devices to an arbiter. We can either use a star-like topology or we can use a daisy chain topology. Let us discuss both the schemes in the subsequent sections. In this centralized protocol, we have a single central entity called the arbiter. It is a dedicated piece of circuitry that accepts bus requests from all the devices that are desirous of transmitting on the bus. It enforces priority and fairness policies and grants the right to individual devices to send data on the bus. Specifically, after a request finishes, the arbiter takes a look at all the current requests and then asserts the bus grant signal for the device that is selected to send data. This selected device subsequently becomes the bus master and gets exclusive control of the bus. It can then configure the bus appropriately and transmit data. An overview of the system is shown in figure 13.24. We can follow two kinds of approaches to find out when a current request has finished. The first approach is that every device connected to the bus transmit for a given number of cycles n. In this case, after n cycles have elapsed, the arbiter can automatically presume that the bus is free and it can schedule another request. However, this might not always be the case. We might have different speeds of transmission and different message sizes. In this case, it is the responsibility of each transmitting device to let the arbiter know that it is done. We envision an additional signal bus release. Every device has a dedicated line in the arbiter that is used to send the bus release signal. Once it is done with the process of transmitting, it asserts this line, sets it equal to 1. Subsequently, the arbiter allocates the bus to another device. It typically follows standard policies such as round robin or FIFO. If we have multiple devices connected on a single bus, the arbiter needs to be aware of all of them and their relative priorities. Moreover, as we increase the number of devices connected to the bus, we start having high contention at the arbiter and it becomes slow. Hence, we wish to have a scheme where we can easily enforce priorities, guarantee some degree of fairness, and not incur slowdowns in making bus allocation decisions as we increase the number of connected devices. The daisy chain was proposed with all the requirements in mind. Figure 13.25 shows the topology of a daisy chain based bus. The topology resembles a linear chain with the arbiter at one end. Each device, other than the last one, has two connections. The protocol starts as follows. The device starts out by asserting its bus request lines. The bus request lines of all devices are connected in a wide OR fashion. The request line that goes to the arbiter essentially computes a logical OR of all the bus request lines. Subsequently, the arbiter passes the token to the device connected to it if it has a token. Otherwise, we need to wait till the arbiter gets the release signal. Once the device gets a token, it becomes the bus master. It can transmit data on the bus if required. After transmitting messages, each device passes the token to the next device on the chain. This device also follows the same protocol. It transmits data if it needs to, otherwise, it just passes the token. Finally, the token reaches the end of the chain. The last device on the chain asserts the bus release signal and destroys the token. The release signal is a logical OR of all the bus release signals. Once the arbiter observes the release signal to be asserted, it creates a token. It reinserts this token into the daisy chain after it sees the request line set to 1. There are several subtle advantages to the scheme. The first is that we have an implicit notion of priority. The devices that is connected to the arbiter has the highest priority. Gradually, as we move away as we move away from the arbiter, the priority decreases. Secondly, the protocol has a degree of fairness because after a high priority device has relinquished the token, it cannot get it back again until all low priority devices have gotten the token. Thus, it is not possible for a device to wait indefinitely. It is easy to plug in and remove devices to the bus. We never maintain any individual state of a device. All the communication to the arbiter is aggregated, and we only compare our functions out for the bus request and bus release lines. The only state that the device has to maintain is the information regarding its relative position in the daisy chain and the address of its immediate neighbor. We can also have purely distributed schemes that avoid centralized arbiter completely. In such schemes, all the nodes take decisions independently. However, such schemes are rarely used, and thus we should refrain from discussing them. Up till now, we have only been focusing on unidirectional communication, where only one node can transmit to the other node at any single point of time. Let us now consider more realistic buses. In reality, most high-performance I/O buses are not multi-drop buses. Multi-drop buses potentially allow multiple transmitters, albeit not at the same point of time. Modern I/O buses are instead point-to-point buses, which typically have two endpoints. Secondly, an I/O bus typically consists of two physical buses such that we can have bidirectional communication. For example, if we have an I/O bus connecting nodes A and B, then it is possible for them to send messages to each other simultaneously. Some early systems had a bus that connected to the processor directly to the memory. In this case, the processor was designated as the master because it could only initiate the transfer of a bus message. The memory was referred to as a slave, which could only respond to request. The memory was referred to as the slave, which could only respond to request. Nowadays, the notion of a master and slave has become diluted. However, the notion of concurrent bidirectional communication is still common. A bidirectional bus is known as a duplex bus or full duplex bus. In comparison, we can have a half duplex bus which only allows one side to transmit at any point of time. So definition 152 full duplex bus. Hold on. It is a bus that allows both of the nodes connected at its endpoint to transmit data at the same point. It only allows one of its endpoints to transmit at any point of. Okay, so half duplex bus only allows one of its endpoints to transmit at any point of time. Let us take a typical scenario of duplex communication between the memory controller chip and the DRAM module in figure 13.26. Figure 13.26 shows the sequence and timing of messages for a memory read operation. In practice, we have two buses. The first bus connects the memory controller to the DRAM module. It consists of address lines and lines to carry dedicated control signals. The control signals indicate the timing of operations and the nature of operation that needs to be performed on the DRAM arrays. The second bus connects the DRAM module to the memory controller. This contains data lines to carry the data read from the DRAM, and timing lines to convey timing information. The protocol is as follows. The memory controller starts out by asserting the RAS row address strobe signal. The RAS signal activates the decoder that sets the value of the word lines. Simultaneously, the memory controller places the address of the row on the address lines. It has an estimate of the time it takes for the DRAM module to buffer the row address. After T row units of time, it asserts the CAS signal, column address strobe, and places the address of the columns in the DRAM array on the bus. It also enables the read signal indicating the DRAM to the DRAM module that it needs to perform a read access. Subsequently, the DRAM module reads the contents of the memory locations and transfers it to its output buffers. It then asserts the ready signal and places the data on the bus. However, at this point of time, the memory controller is not idle. It begins to place the row address of the next request on the bus. Note that the timing of the DRAM's access is very intricate. Often the processing of consecutive messages is overlapped. For example, we can proceed to decode the row address of the n+1th request when the nth request is transferring its data. This reduces the DRAM latency. However, to support this functionality, we need a duplex bus and a complex sequence of messages. Let us note a salient feature of the basic DRAM access protocol that we showed in figure 13.26. Here the request and response are very strongly coupled with each other. The source memory controller is aware of the intricacies of the destination DRAM module. There is a strong relationship between the nature and timing of the messages sent by both the source and destination. Secondly, the I/O link between the memory controller and the DRAM module is locked for the duration of the request. We cannot service an intervening request between the original request and response. Such a sequence of messages is referred to as a bus transaction. A bus transaction is defined as a sequence of messages on a duplex or multi-drop bus by more than one node. When there is a strong relationship between the messages in terms of timing and semantics, it is in general not possible to send another unrelated sequence of messages in the middle and then resume sending the original sequence of messages. The bus is locked for the entire duration. There are pros and cons of transaction-oriented buses. My internet is fluctuating again. I will just stream for a little while more and then I will end the stream because my internet is going down again. There are pros and cons of transaction-oriented buses. The first is complexity. They make a lot of assumptions regarding the timing of the receiver. Hence, the message transfer protocol becomes very specific to each type of receiver. This is detrimental to probability. It becomes very difficult to plug in a device that has definite message semantics. Moreover, it is possible that the bus might get locked for a long duration with idle periods. This wastes bandwidth. However, in some scenarios, such as the example that we show, transaction-oriented buses perform very well and are preferred over other types of buses. Let us now look at split transaction buses that try to rectify the shortcomings of transaction-oriented buses. Here we do not assume a strict sequence of messages between different nodes. For example, for the DRAM and the memory controller example, we break the message transfer into two smaller transactions. First, the memory controller sends the memory request to the DRAM. The DRAM module buffers the message and proceeds with the memory access. Subsequently, it sends a separate message to the memory controller with the data from memory. The interval between both the message sequences can be arbitrarily large. Such a bus is known as a split transaction bus, which breaks a large transaction into smaller, shorter individual message sequences. The advantage here is simplicity and probability. All our transfers are essentially unidirectional. We send a message and then we do not wait for its reply by locking the bus. The sender proceeds with other messages. Whenever the receiver is ready with the response, it sends a separate message. Along with the simplicity, this method also allows us to connect a variety of receivers to the bus. We just need to define a simple message semantics. And any receiver circuit that conforms with the semantics can be connected to the bus. We cannot use this bus to do complicated operations such as overlapping multiple requests and responses and fine-grained timing control. For such requirements, we can always use a bus that supports transactions. I'll read about the network layer in the next stream. Anyways, I will end the stream here then, and yeah, I'll see you guys next time. Bye.